Hello, so in this video we're going to talk a little bit about hexadecimal numbers. Now you're probably already familiar with binary numbers like this one, and the way we convert a binary number is if we have a 1 column, a 2 column, a 4 and an 8, then we simply add up. We've got 1 8, 1 2 and that gives us 10. If you need to know more binary numbers, have a quick search for that first, because it's quite important you get binary numbers before you try to look at hexadecimal numbers. So hexadecimal numbers, the idea is we have here one nibble. A block of 8 binary digits is referred to as a nibble. And we use nibbles a lot in computer science. So we can store any number from 0000, which is 0, to 1111, which is 15. So there are 16 possible values from 0 to 15 that we can store in a nibble. And as humans, it can get quite messy when you see a whole page full of ones and zeros. It's really easy to make a mistake, to write one of them down incorrectly, to miscount how many we've got. So binary is great for computers, and everything in a computer is still stored in binary. But for humans, it can be handy to store things in a format where each nibble could be represented using a single digit. So how can we have a single digit that goes everywhere from 0 to 15 and can store every possible value? Well, we need to be able to store 16 values. So the first 10 are pretty straightforward. 0, 1, 2, 3, all the way to 9. We can just write down the normal numbers, that's easy. Once we get to 10, we can start using letters instead. So 10 would be A, 11B, 12C, 13D, 14E and 15F. So those are the hexadecimal numbers, and what this means is for each of these you can have a binary nibble, a hexadecimal character or a denary number, and they all mean exactly the same thing. It's just a slightly different way of representing it and writing it down so that it's easier. So in everyday life we use denary because that's what people count in. That's how humans count. Computers can only turn things on and off, so we have things in binary. And those are the two basic number systems that we use. Binary inside the computer, denary when it's humans talking to other humans. Hexadecimal is handy because each nibble maps neatly to one digit and each digit maps neatly to one nibble. So it makes conversion very straightforward, and it's also much easier to remember the hexadecimal version of each digit than the binary code, because it's quite hard to remember exactly which order of ones and zeros, and it gets quite repetitive. So it's better for humans than binary because it's easy to remember and you're less likely to make a mistake, and it's better for computers than denary because each digit maps nicely into one nibble. So that's what hexadecimal is, and most people seem to get the hang of that pretty well. So in an exam, if you get asked a hexadecimal question, as soon as you see this hexadecimal involved, the best thing to do is write that table out in the corner, in the margin, somewhere out of the way. So nobody's going to mistake it for your answer, but it's a useful thing to look at and make sure you don't make any mistakes. So how do you convert hexadecimal back to denary? Well, if it's a single digit, that's quite easy. A D, you just look at the table, it's 13. I should write these are all hexadecimal and these ones are all denary. Right, so if you had an E, just look at the table and say, right, well that's 14. And that's really straightforward. The tricky bit comes when you have two hexadecimal digits. So let's say we have the number 2D. So how do you convert hexadecimal 2D into a denary number? Well, if you think of binary numbers, I'll go back to the one I started with right at the very start. You write across the top 1, 2, 4, 8. You start with a 1 and you double it and you double it and you double it. And that's how you do the headings for the binary numbers. Well, if you're writing in denary numbers, let's say we have 7, 8, 9. Then you have 1 times it by 10 times it by 10. So it's 7 hundredths, 8 tens and a 9. So again, that's pretty straightforward. When hexadecimal, you do exactly the same thing. You put a 1 up here and a 16 up here. And The good thing is you'll never be asked to do more than 2 digits at GCSE level, or frankly at A level either. So you've got your 2-digit hexadecimal code, or your 2-digit hexadecimal number. Right, your numbers across the top, 1 and 16. So you've got 2 16s, well that's 32. 1 D, D is 13. Add those up, and you get 45. And there's your answer. So we'll do one more. And it really is that easy. So I'll do a harder one this time. If I do A7, how on earth are we going to do that? Well, we write 1 across the top and 16 there. Left hand side we do 16 times A. A is 10. So we've got 16 times 10 is 160. We've got 7 ones. So we don't need to write that one out. We can probably do that one in our heads. Add those up, you get 167. And that hexadecimal code A7 is equal to 167 in denary. So if you think you've got the hang of those, then here are some hexadecimal questions for you to have a go at. On the left hand side here we've got convert to denary from hexadecimal, and we've got 4 that are single digits and 4 that are double digits. And over here, you don't normally get these at GCSE level, but it's worth a go just to see if you understand it. Can you convert these numbers from denary into hexadecimal and get those answers right? So have a go at those on a piece of paper, and then have a look in the notes for this video, and I'll put the answers in there for you to double check afterwards.